All right, welcome. In this video, we are going to talk about deviations from the ideal gas law. And yeah, so we've been talking about the ideal gas law, which is the, PV equals nRT. And this equation, works well when you're dealing with an ideal gas. We want to talk about what it means to be an ideal gas. And there's some assumptions we make that in order to make the ideal gas law work. Two of those main assumptions we make is that the volume of the gas particles themselves are small compared to the space between the particles, and that the forces between the particles are not significant. So basically, that there's essentially no intermolecular forces between the particles, and that the volume of the gas particles themselves, that they have like no volume on their own. So basically that, they are so spread out that the volume of the individual particles themselves are insignificant. Sorry, my handwriting's messy. Okay, and so, yeah, that's what it means to be some of the assumptions we make about ideal gases. And these assumptions work pretty well under standard conditions. So these assumptions work when gas particles are very spread out. So when they're really spread out, the volume of the individual particles is negligible, and the molecules experience almost no intermolecular forces because they're so spread out. But if you're under high pressure or low temperature conditions where these particles are jammed a little bit closer together, these ideal gas assumptions start to break down. And we start to see deviations from what we'd expect to see from ideal gases. And if you think about why this happens, so under high temperature, and or low pressure conditions, the molecules are really spread out. The volume's mainly empty space. The volume of the individual gas molecules then is insignificant. And the intermolecular attractions between molecules are insignificant because they're so far apart, they're not really experiencing those intermolecular forces. This over here is an ideal gas. Over here, under these high pressure and or low temperature scenarios, the molecules are going to be much closer together, and then the volume of the particles becomes more significant, relevant to the total amount of space they're occupying. And since they're close together, the molecules are going to experience more intermolecular forces of attraction. And so here we'll see some deviation from ideal behavior. So again, here this summarizes the ideal gas law calculation. So, PV equals nRT works when we have the following assumptions: that the individual gas molecules have zero volume and they experience zero attractive forces. These assumptions in general are not bad assumptions, but they start to break down when the gas is under high pressure and or low temperature conditions. Under these conditions, the gas particles are relatively close together. And then these assumptions become kind of problematic when those particles are close together. What are some of the effects we will see? Well, when we measure the pressure of a real gas, it will have less pressure than predicted from the ideal gas law. So if we were to, here's ideal gas law, PV equals nRT. If we were to do a calculation and solve for pressure, this would tell us the pressure we would expect an ideal gas to form. A real gas is going to exert pressure a little bit smaller than this number. And that's because real gases actually do experience intermolecular forces. And due to those intermolecular forces, those particles will spend, if they're attracted to each other, then they're going to spend a little bit more time interacting with each other and less time bumping into the walls. So therefore, we will observe less pressure. So we'll observe lower pressure than expected due to those intermolecular forces of attraction there. And we'll notice this more with molecules that experience stronger intermolecular forces. So the stronger the intermolecular force, the more dramatic this impact will be, and you'll see a larger decrease in the expected pressure. So here is a kind of visual showing this. This is ideal gases in red, and here's xenon. You can see the actual pressure of xenon is a little bit lower than what we would predict it would be. Volume effects. So remember, with ideal gases, we assume the particles have no volume, but real gases, the particles do have volume, right? They take up space. Therefore, a real gas is going to take up more space than we'd expect it to. because the volume of those individual particles is going to contribute to the overall volume. But this is only really going to be noticeable at those high pressure conditions. So here's a graph showing volume of pressure. The red is the ideal gas line. Green is argon. And you can see that under high pressures, the volume's higher than we would predict it to be for an ideal gas. But when we're talking high pressure, we're talking very high pressure, like over 200 atmospheres. And remember that standard conditions at sea level is 1 atmosphere of pressure. So generally, under standard conditions, the ideal gas law works pretty well. It's really under these like high pressure situations that we start to see more deviation from ideal behavior. So this kind of gets what I was just talking about here. So these differences or deviations from ideal behavior are only noticeable at really high pressures and low temperatures. So these are going to be significant in certain applications, but for us, when we're carrying out reactions at room temperature, we tend to not have to worry about these deviations, and we can just use the ideal gas law. Okay, so in most cases for us, assuming a gas is ideal works just fine. So what do we need to do with this information? So here's some practice problems that we might need to be able to, some questions we might need to be able to answer. Okay, so here's some examples. Predict which situation would show the greatest deviation from ideal behavior. So scenario 1 would be you might predict it based on pressure and temperature conditions. And we know that we are going to deviate more under low temperature and or high pressure situations. Those are the situations when the molecules are really tightly packed together. So it looks like this is a really high pressure and low temperature condition. So I'm going to expect it to, this sample to behave less ideally. So it's going to deviate more from ideal behavior. This gas would behave more ideally. Okay. Another comparison we want to be able to do is to predict who's going to deviate more from ideal behavior based on their intermolecular forces. So if you look over here, hydrogen gas, it's a small nonpolar molecule, only experiences dispersion forces. NH3 is larger and it experiences hydrogen bonding. So your NH3 is going to deviate more from the ideal behavior, really for 2 reasons. One is it's a larger molecule, so it's deviating more from that assumption that the molecules have no volume. So NH3 has more volume than H2, and it has stronger intermolecular forces, the hydrogen bonding versus the dispersion forces in hydrogen gas. All right, so the stronger the IMF is going to deviate more. Okay, so here's some more practice problems here. So which sample would deviate most from ideal behavior? So who would behave least like an ideal gas? So notice how the things you want to look for is look at the intermolecular forces, and we want to look at the pressure temperature conditions. And these are all neon, so they're all the same gas. They all have the same intermolecular force. So I'm going to instead focus on the pressure and temperature. And we know that gases tend to deviate from ideal when they have either strong intermolecular forces or if they're at a very high pressure and or low temperature conditions. So I'm going to look for the high pressure. That would be either this one or this one, and I'm going to pick the one that has the lowest temperature of them all. So this is going to be my correct answer here. This will behave the least ideally. Okay, here's another one. Who's going to deviate the most from ideal behavior? So remember again, the ways we deviate from ideal, if we have relatively strong IMFs, or if we're at very high pressure or low temperature. And these all have the same pressure temperature conditions. So here we want to be looking at the intermolecular forces. These ones are all, the first 3 are all nonpolar. They all experience dispersion forces. This one right here is polar, and it is so it experiences dipole-dipole forces. So we'd expect this one to have the largest deviation from ideal behavior because it's got the strongest intermolecular forces. Okay. It's also important to notice too, it's also one of the larger molecules as well, because we also want to consider the strength of the dispersion forces too. Okay, so the argon gas deviates more from ideal behavior than neon gas. What's a reason for this difference? Well, if you look at neon and argon, neon is above argon on the periodic table, so we know that neon is going to have a smaller radius. Neon only has 2 shells. It looks like argon has 3 shells. So that first option that says IMFs for neon stronger than that of argon, that doesn't really seem to fit because they both have dispersion forces. And if anything, neon's going to have weaker dispersion forces because it's got a smaller electron cloud. The argon atoms are more attracted to the walls of the container. Huh? That seems a little weird. Are they attracted to the walls of the container? Okay, I'm going to ignore that one. The particle volume of argon is greater than that of neon. Well, that seems to fit with what we know here, so let's kind of hang on to that one. And how about this? Argon atoms have more valence electrons than neon atoms do. Well, that's not true. They both have 8 valence electrons. So it's not this one. So it seems like C is our best choice, and that makes sense because remember, we assume that ideal gases have no volume. Like no particle volume, right? So the volume of the individual particles is insignificant compared to the space. So the larger these individual particles are, the more it will deviate from ideal behavior. So this is like what our ideal gas would look like. This is maybe what a non-ideal gas would look like. So the more space those individual particles take up, the more it will deviate from ideal behavior. So here's another one. Basically, who's going to deviate more from ideal behavior? So we know that they tend to, that ideal gases tend to be very spread out. And that's why they experience no intermolecular forces here. So this gas over here seems to be more ideal because its particles are more spread out. Over here, this one is less ideal. So it looks like sample 2 is going to deviate more from ideal behavior because the atoms are closer together, so they're going to experience those intermolecular attractions more strongly. And so it will behave less ideally because, again, remember the ideal gas, they're spread out and they experience no intermolecular forces. All right. So I hope that video helps. Let me know what follow-up questions you have.